All right, everyone, looks like it is just about time for us to be getting started. So I'd like to take this moment to welcome you all to the Morrison Planetarium. My name is Rook. I'm going to be your presenter today for this tour of the universe. Now, before we can get started, I'd like to issue a couple of reminders about our planetarium. So first, I'd like to ask you all to please remain seated for the duration of the show. Please do not get up to try and move or shuffle seats or to attempt our very steep stairs in the dark. We also ask that your mask stay securely fastened around both your mouth and nose during the show. And to that end, there is no eating or drinking here in the planetarium. Make sure any food or drink you have stays sealed up and put away. Also, a wonderful time to silence and stow those electronic devices. Anything you have that makes light or sound or records audio, video, or photography should be put away during the show. And lastly, if you start to experience any motion sensitivity during the show, our typical recommendation is to sit back, relax, close your eyes. While this is a very immersive experience, the dome is never actually moving, so the feeling should subside momentarily. But if you need to make an early exit for any reason, please use the exits at the top of the planetarium, up the stairs, and not the exits at the bottom where you came in. And with that, I think it is just about time for our tour of the universe to get started. This is our live show of the day. It means it's got live visuals provided by a science visualization software and live audio provided by yours truly. Now, I'd like to give our science visualization software today a particular shout out because it's a little bit unique among softwares used in planetariums. It is open source. This means it is free for you to download and try out for yourself. It's called OpenSpace. You can find it at OpenSpaceProject.com if you'd like to give it a try. That is OpenSpaceProject.com. And how science visualization software works is it takes data that we have about the universe around us. This could be anything from the positions of nearby stars to photographs of planets like our very own planet Earth taken by satellite, and it uses those to create a three-dimensional environment that we are going to be able to explore. So a science visualization software is one way that we can explore space, but it isn't the only way. Now, one of the ways that I feel most captures the imagination is by putting on a spacesuit and going to do it yourself. A lot of people imagine space exploration that way, done by astronauts who go into space in person. But it turns out exploring space in person is actually something we only do very rarely. If you are an astronaut these days and you are going to space, you've probably got one particular destination in mind. So that destination will be our first stop for our tour today. We are heading to Earth's largest human-made satellite. I can show you its orbit as it circles the Earth right there. That little yellow line marks the orbit of this satellite. And I call it the largest human-made satellite because it turns out anything that orbits a planet is called a satellite, whether people made it or not. So moons fall into this category. Our moon is a satellite. And this falls into that category. It's made by people, making it our largest human-made satellite. And it's called the International Space Station. It's not just a satellite, it is a research center up here among the stars. It is a place for humans to live and work in space. We're not all that far from home. You can see Earth right there in the background. But up here, the environment is very different from the environment you experience when you're safely on the surface of our planet. Up here, there isn't really any gravity to speak of. There is no oxygen to breathe. And the astronauts up here aren't protected like we are by the blanketing atmosphere, keeping us safe from things like radiation coming from space. So space is a difficult place to be. And that's part of why the International Space Station exists. It allows us to test ways to survive in space for long periods of time. The longest a single astronaut has been up here for a stretch is about a year. And that's because when it comes to traveling through space for humans, it takes a really long time to get most everywhere. It takes days for people to get from Earth to the moon. It could take months or even years for us to travel to another planet. So as we prepare to make those leaps, the International Space Station is a wonderful way for us to experience space, to test out living in space, and to learn how to do it for those long durations of time. Up here, you'll find not only astronauts, but also things like plants or microbes as we test how things that live here on Earth survive in this very, very different environment. And As you can imagine, for all of those reasons, traveling through space as humans, going there in person, is pretty rare. And we haven't actually done it that much. We haven't gone particularly far. The furthest humans have ever gone away from Earth is just to our own moon, still technically within the planet's orbit. So I'm going to show you the orbits of the planets as they go around the sun, and I'm also going to show you the orbit of the moon as it goes around the Earth. These blue lines mark the orbits of the planets, and you'll see around our planet a smaller blue line that encircles our Earth. That marks the orbit of our moon. That is the path it takes as it circles our planet. And that is the furthest human beings have ever gone. So that little blue circle, that marks the boundary between all of the places in space that human beings have been and all the places that we haven't. So as we go here, beyond that little blue line, as we go further and further away from Earth, a lot of the information that we have, we didn't gather in person. We got it other ways, by relying on other travelers. One of the most common things we rely on when it comes to exploring space beyond our own planet is light. Light, indeed, will travel through space. Light will travel everywhere it goes. Here on Earth, this is a little bit hard to tell because it travels very, very quickly. Light is the fastest known thing in the universe. If I turn on my little laser pointer, for instance, it seems to me that the light appears instantaneously. But that's not quite the case. It does have to travel from my laser pointer all the way over to the dome and then back to my eyes for me to observe it. This happens so quickly that I can't even tell. But out here in space, that's going to change. So, for instance, it takes about 8.5 minutes for light to travel from our sun all the way to our own planet Earth. So, if you were to observe the sun, preferably using a solar telescope or suitable eye protection, you're looking at the sun as it appeared 8.5 minutes ago because you're seeing light that left the sun at that time. If the sun were to suddenly turn green, you wouldn't know about it until 8.5 minutes later. That's how long it would take that new green light to make its way all the way to planet Earth for us to observe it. And 8.5 minutes doesn't seem like a terribly long time, but as we get further and further away from our own planet, that distance is going to start to become immense. We tend to use a unit of measurement that has to do with light as we get further and further out into space. We call it a light year. It's a measurement of distance, and it measures how far light will travel if you give it a year to do so. We are not yet a light year away from Earth. In fact, we're not even close. But we're going to stay here at the edge of our solar system because it turns out humans and light aren't our only means of exploring space. Quite a lot of space exploration is also done by robots that go into space all on their own. So you might have heard about Perseverance, the robot that is currently cruising around on Mars, and other robots go even further. I'm going to show you some of the furthest that have ever traveled away from Earth. This maneuver always takes the computer a moment or two because it's actually fetching the position of those rovers right now. So everything I'm showing you is in real time, one of the cool parts of our software, which means that where you see the planets around the sun, that's where they actually are. Same with these rovers. So these yellow lines mark their paths as they head away from planet Earth. Here you can see the Pioneer probes, the New Horizons probe, and then the two furthest lines. Those mark the paths of Voyager 1 and Voyager 2. Voyager 1 is currently the furthest anything made on Earth has ever gotten away from our planet. And it's about 19 light hours away. So it takes light 19 hours to get from Earth over to Voyager 1. It takes about 19 hours for light to get back. This is important because we don't just use light to see, we also use it to communicate. We speak with robots like Voyager 1 using things like infrared light or radio waves, two forms of light that human beings can't see, but that we can use technology to communicate through. So, if we wanted to send a message to Voyager 1, it'd take 19 hours for that message to get there. It would take 19 hours for Voyager 1's message to get back to us, all traveling at the speed of light. Now, Voyager 1 is thought to be just outside of our solar system now, so we'll call that the boundary where our solar system ends and interstellar space, the space between stars, begins. And it's worth noting Voyager 1 has been making that journey for around 50 years now. That little robot has been traveling for half of a century, and it's covered the same amount of distance that light can cover in less than a day. So as we get further away from our planet, as we pass that boundary, past Voyager 1, we rely almost exclusively on light to learn about the rest of the universe. And the distances out here are going to start to get truly immense. The closest star to our own, a star named Proxima Centauri, is 4 light years away from Earth. That means also that as we look at Proxima Centauri, we see it as it appeared 4 years ago. And if we wanted to send a message to Proxima Centauri, it would take 4 years to get there. It would take 4 years for Proxima Centauri, if it so chose, to send a message back. Imagine if you started texting Proxima Centauri the moment you were born, how many lines long would your conversation be by now? So now we're here in interstellar space, seeing our surrounding stars, and currently the idea of sending messages to other stars and getting anything back is a little bit far-fetched, but we are starting to learn a lot about our interstellar neighbors. We're starting to learn that a lot of the things we thought were unique about our solar system kind of aren't. They're actually quite common. For instance, many of these stars have planets orbiting around them. We think, in fact, that the average sun-like star, the average star that looks like our sun, has around 10 planets orbiting it. Our solar system might even be unusually small. So as we find more and more of our planets, I can show you just some of the planets that we found around these other stars. We've found more than 4,000 so far, and that exact number is probably already out of date because we're finding more and more all of the time. And now we're going to start to head even further than interstellar space. We're going to start to head into intergalactic space, the space between galaxies. But before we get there, I'd like to pause, and I'd like to observe the sky as we've observed it for thousands of years, because for thousands of years, we have been doing what we're still doing now, using light to learn about the universe around us. So for a moment, let's imagine that, let's say we're astronomers from a couple hundred years ago. And you, astronomer from a couple hundred years ago, you have a view of the sky not too dissimilar from this, and you would like to know more about it. You would like to know what the universe is and what your place within it is. The whole of the universe is just what you can observe from on Earth, looking up at the sky with your newfangled telescope. So you do the sensible thing. If you would like to map the universe, you take out your telescope and you start counting stars. You assume that the brightest stars are going to be closest to you. The dimmest stars are going to be furthest away. This isn't entirely accurate. Some stars are just dim or bright all on their own, but it will get you where you're going. And astronomers using this method actually did make some important discoveries about what to them was the known universe. They noticed, for instance, that what they were inside was a disk. All the stars around them seemed to behave kind of like a flat pancake full of stars, a flat circle. But as they created their maps, something bizarre started to happen. It started to be the case that the furthest stars they were able to observe in every direction stretched an equal distance away from Earth. In short, it began to look on their maps like our solar system and our planet were right in the center of the universe. Now, I hate to break this to you, astronomer from a couple hundred years ago, that's not quite true. But why did it look that way? It wasn't as if these astronomers put our solar system at the center because they wanted it to be and because they were full of themselves. That's what the data they were observing as they looked up at the stars told them. So why is the conclusion they drew wrong? A part of it comes down to the fact that we can only ever see so much. As they were looking up at the stars, they were thwarted by the very galaxy they were within. So as you look up at the Milky Way galaxy, you might notice this huge stretch of incredible, dramatic, beautiful clouds that seem to stretch across the sky, across all of those stars. And it turns out those clouds were the problem. As we look through the Milky Way, we can see clouds of dust and gas. These things, as you are inside of them, seem pretty spread out. But as you try to look further and further, they begin to obscure your vision. It's a bit like looking through a dense fog. The reason those old maps looked the way they did was because the astronomers could only see the stars in their immediate neighborhood. Now, these days, we can see a whole lot more. We know that all these stars around us, these are not the known universe. These are just a small part of a larger structure, our Milky Way galaxy. And I can show you a good approximation of what that galaxy looks like now, as we've gotten better and better at observing what's around us. And this is the part where I would love to tell you that we've got it all figured out, that this is a 110% completely accurate version of the Milky Way galaxy, and we're never going to make any mistakes ever again. But that's also still not quite true. In fact, this isn't a picture of the Milky Way galaxy, at least it's not a photograph of it. We can't take a photograph of our galaxy from this angle, because in order to do so, we'd have to send a camera all the way out here, outside of the galaxy. And remember, the furthest thing we've ever sent away from Earth is just outside our own solar system. So how do we know what our galaxy looks like? Or at least how can we make this guess? Well, like I said, we have known some things for a long time. We know it's shaped like a disk, a flat circle. We can also see these spiraling arms stretching away from the center as we see stars clustered together with voids in between where not a whole lot seems to be going on. We know that in the center of our galaxy are bright, old stars, so bright their light can be seen all the way from Earth, so bright that we can see them from distant parts of the galaxy, and we can see them orbiting rapidly around something with incredible mass that sheds no light, which we can only assume is our very own supermassive black hole. We also have a secret weapon when it comes to determining what our galaxy looks like. We know that our galaxy shares a lot of its structure with other spiral galaxies. And yes, you heard me right. I said other spiral galaxies. Our galaxy is far from the only one. So as you see these technicolor dots start to appear, these are not stars. Each of these dots marks the location where astronomers have found another galaxy. Some of these galaxies, like Andromeda or the Whirlpool Galaxy, are close enough that we can get photographs of them in great detail. And they share their structure with the Milky Way. Both of those are spiral galaxies. So we can use them to determine what our galaxy likely looks like. And we can see much, much further than those nearby spiral galaxies. In fact, now I can show you a very different view of our known universe. And every single dot here, it's important to remember, is a real galaxy. These dots have all been observed by astronomers here on Earth. And this is what they see. Now, once again, we're faced with a pretty peculiar map of the universe. So there's a couple things of note here. The first is that once more, it looks like where we just came from, our galaxy is right in the center of our map, right in the center of the known universe. But it also looks rather like our galaxy is shaped like a butterfly or a bow tie. We've got these huge voids here where we don't see any other galaxies at all. And the first thing can be explained by the fact that this is just what we can see from our vantage point. There's a lot beyond this that we can't see for a lot of reasons that I'll get into once we're out there. And these voids, this peculiar shape it takes, well, it turns out all that dust and gas in the Milky Way is still causing us problems. So the reason these voids exist is because this is where the disk of the Milky Way lines up. In order to see what's on this side and this side, we have to peer through all of that dust and gas in our galaxy in order to see what's on the other side. And that's a pretty difficult thing to do, something we're still working on. You might notice a couple intrepid surveys have managed to do just that, and they're finding just as many galaxies within these parts that we can't see as there are in the parts that we can. So it's likely all of this map might one day be filled with galaxies, just as filled up as the parts that we've currently mapped. We just haven't found all those galaxies yet. So there's always more for us to observe, for us to discover, and for us to work on. Now, we're going to get even further away. We are quite far away from Earth right now. We are, I think, a couple billion light years away from our planet. And because of that, the way that we observe the sky using light, which has to travel from place to place, is going to have a pretty big impact on what we're able to see as we get further away. Remember how I said when things are very distant, as we look up at them, we see them how they appeared a couple years ago? So if we look up at Proxima Centauri 4 light years away, we see it as it looked 4 years ago. Well, out here, billions of light years away, we start to see something pretty incredible. You might notice these dots have changed from blue to red, and that's because we're actually showing you something different. These are no longer galaxies. These are something called quasars. We know that they're bright, they're hot, they're dense. We don't know a whole lot else about them because they're so difficult to observe. But we do suspect that these are infant galaxies. These are what galaxies used to be before they obtained the structure that we know them for now. And we can see them because light that's coming to us from this part of the universe is billions of years old. There might not be any quasars in the universe anymore. It's possible they've all grown up by now. But we can still see them because that old light is still making its way through the universe. That old light is still there for us to observe. That means that we get to look at an archive of the universe's history as we look further and further away, and as we observe older and older light. We can look into the past. This, I think, is very, very, very cool. But unfortunately, it's also going to spell the very last stop on our trip today. Because as we peer into the past, we're going to reach a point that we just can't look any further than. And this is that point. This is something called the cosmic microwave background. We call it microwave because it can be observed in microwave light, which is another form of light, like radio and infrared, that can't be seen by our eyes, but that can be seen by technology like telescopes. This cosmic microwave background is made up of light that's around 13.8 billion years old. And if you're keeping track, 13.8 billion years ago is about when the Big Bang occurred. This light was created maybe a couple 100,000 years later, and this light is still traveling through the universe today. So this light is light left over from when the universe was brand new. It's some of the first light that was ever created, and we can still observe it even all the way back on Earth. We can see some of the earliest light there is, and track the universe almost all the way back to its very beginning. Unfortunately, we can't go further than this because if there is more stuff further than this, maybe more galaxies like the ones we see back home, if we want to see the light that those things are emitting right now, we'd have to wait another 13.8 billion years for that light to make its journey all the way to our planet. I don't know about you, but I have other plans for the evening. So maybe instead it's time for us to head home. And that can be a kind of disappointing note to end on, right? The idea that maybe there are some things that we might never be able to see, not because we're not trying hard enough, not because our technology isn't good enough, but just because of the way that the laws of physics work. But remember, as we're heading back home, as we head past the cosmic microwave background, as we head past these quasars, galaxies in their infant form, and as we head past the neighboring galaxies that we can observe from Earth, each one of these dots represents something that's really out there in space. Each one of these dots represents the work of astronomers who have been looking up and waiting as that light makes its billion-year-long journey to our planet. There are people here who are just waiting to see it. And imagine what those astronomers from a couple hundred years ago would think if they could see our map of the universe today, stretching not just past all of those nearby stars, not even just past our galaxy, but past time and space to the very beginning, or nearly the beginning, of the universe. And that's something that you can be a part of any time that you decide to look up at the sky. The stars around you might not be shedding light from billions of years ago, but you'd be surprised at how old some of the light that you're looking at is. You might be seeing light that's traveled for years, maybe decades, maybe centuries, maybe even thousands of years to reach you. And you can be the person who gets to greet it after that 1,000-year-long journey as it finally makes its way to Earth. Now, as we make our way back to our own planet, and into our own solar system, that is where our show is going to conclude. A couple of reminders before we do stop. Our exits today are going to be at the top of the stairs, so once the lights come all the way up, make your way to the exits at the very top of the stairs. If you cannot climb the stairs for any reason, please remain seated and a staff member can assist you through a lower exit. If you have any questions or comments, my name is Rope. You're welcome to stop by and say hi. If there's anything you'd like to know or anything you'd like me to know, I'd be happy to hear any questions you have or any feedback you have about the show. And otherwise, as we finally catch a glimpse of our very own planet, I would like to thank you on behalf of myself and the entire Morrison Planetarium for joining us for this tour of the universe.